So let's say that again. Hooke's law. Hooke's law describes the restorative force that acts on a spring if I try to distort it. And so that restorative force acting on my hand in this case, or it could be restorative force acting on a mass. If it's the mass that's distorting the spring, but the force acting to the left in this case is exerted by the spring, while the other force is being exerted by the mass on the spring. Yes, sir?
Isn't this still your hand exerting the force?
Oh, stop being so picky. You know what I'm talking about. Of course, it doesn't have to be a spring lying on its side. If you use a little bit of imagination, this could be a spring hanging vertically. Right? So we could talk about the force being supplied not by my hand, but by gravity. Okay? And we could figure out what that force is exactly if I happen to know the mass that this mass has. And I could calculate the value using Fg equals mass times acceleration to gravity. So let's finish this up. Hooke's law describes the restorative force that a spring exerts on as another force distorts the spring. So, what was I saying? Oh, that's right. The greater the force is that distorts the spring, and this is going to seem obvious when I say it, the longer the spring gets. Can you believe it? In other words, if I have a spring hanging from the ceiling like this, that's a spring hanging from the ceiling, and I don't hang anything off of it, I could say that it has an unstretched length, L, length. But if I take the same spring hanging from the ceiling, and I hang a little mass off of it with a hook, is it longer? Absolutely. And I could figure out how much longer, because if this is the length, and this is how much its length has increased, we call it a distortion of x. I could find out the x value by subtracting the total length, the new length, taking the old length and subtracting it from the new length, and getting the x value. A little bit of simple math. Okay? I could find out that distortion amount. So what we could say in a proportionality statement is that the applied force is proportional to the amount that a spring stretches. Seems obvious. But what Hooke noticed was this is true, and if he applied many different force values to the same spring, force 1, force 2, force 3, different forces, and you might apply those different forces by hanging different masses off of the same spring, what happened to the x value, the stretch amount? Increased, right? Starting from 0 even, because if you apply 0 force to a spring, how much does it distort? 0. So he ends up getting a graph that looks something like this, with force on the vertical axis and x on the horizontal axis, x with units of meters, and force with units of newtons. The graph looks like this. No problem. It just gets bigger and bigger and bigger, stretch, as you apply more and more and more force. And so what he did with a given spring was find, because what else are you going to do with a straight line? What do you do with it? Find the slope. Make as big a right triangle as you can, as big of a rise over run triangle as you can. You find your delta y, you find your delta x, in this case delta x actually is x, and you find your slope. And it turns out that the slope is going to be constant for a given spring. In other words, for an ideal spring, because it's really Hooke's ideal spring law, for an ideal spring, you keep on pulling, the spring keeps on getting longer at a different rate or at the same rate? Same rate. So for a particular spring, there's a characteristic slope. So what people say is, well, let's find the slope for such a graph for a spring. Find a bunch of F values in a T-chart. Find a bunch of F values, maybe applied force values to a spring. Find a bunch of X values, plot them on a graph, and you get a graph that looks like this. Find the slope. There's something special about that slope. Really what we're saying is, pardon me, if I apply a force, that force is going to be equal to a slope value times the amount that you get a stretch for. And the slope value we end up calling K. You know that old equation we had from grade 9? Y equals mx plus b? This is basically y equals mx plus b, but what's the b value? 0. K is the slope. This is y equals mx plus b, where b equals 0, because it intersects at the 0 point. Okay? And so Hooke said this. Force, we could even say that it's a spring force, is equal to a spring constant, which is just the slope that we just talked about, and every spring has its own spring constant, because every spring has a characteristic slope. If I make a graph like this, every ideal spring, and X is the spring distortion. Or we could say extension, but I'm going to say distortion, because if it was a compression spring, it would still be a distortion. This happens to be an extension spring. Okay? So we've got a situation where a spring hangs from a ceiling. It stretches by a certain amount. It stretches by a certain amount because I apply a force, and if I do that a bunch of times and make myself a table of values for the amount of force I apply to get the stretch values, then I can make a graph, find the slope of that graph, and the slope, as it turns out, is going to describe the relationship between, using y equals mx plus b equation, describe the relationship between how much stretch I'll get for that spring if I apply a certain amount of force. Clear, right? I want to try a free body diagram approach to thinking about this as well. I'll get to that back to you in a second, okay, Thompson? If I want to think in terms of free body diagrams, draw it in red so it sticks out here. If I have a spring attached to this mass, what force can I calculate easily here? Can I easily calculate the spring force? Not really. What I can do, though, is calculate the gravitational force acting downwards on that mass if I have a hanging system. Because it's just mass times acceleration due to gravity, and we've done that lots before. What's special about that Fg value if I just hang a mass vertically from a spring? What's it also equal to? What other force? Yeah? Yeah, you got it. The spring force. Yeah. So it happens to also be equal to the spring force if that thing is sitting there stationary. So I could say, hey, look, I know the spring force, Fs, is going to be equal to the force due to gravity for the hanging mass. So I can get these values, I can develop a table of values quite easily by hanging successively more mass off of a spring and measuring the distortion amount, and I can find out what the K value is for a given spring in that way. Okay? That's all we're going to do today.